first session on deep neural network. Our first speaker is Jakob Forster, and he'll be speaking about DICE, the infinitely differentiable Monte Carlo estimator.
Hey, my name is Jakob Forster. Today I'll talk to you about DICE, the infinitely differentiable Monte Carlo estimator. While I'm a PhD student at the University of Oxford, this work was produced with a set of fantastic collaborators across Oxford and CMU. Recently, deep reinforcement learning has been making the headlines in popular news on an almost daily basis. So clearly we've gotten rather good at estimating first-order gradients in stochastic settings. However, while it's great that we can train agents to solve tasks using a billion samples, wouldn't it be nice if we could also train agents to learn how to solve a broad variety of hard tasks? One potential answer here is meta-learning, or learning how to learn. And indeed, there has been a surge of papers recently that apply meta-learning to reinforcement learning problems. However, when we are doing this, we have to differentiate through the learning step of an agent in an environment. And this leads to the emergence of higher order gradients. And while it's really easy to estimate and to construct the estimator for the first order gradients, constructing the higher order gradient estimators of stochastic computation graphs is a rather painful process that often goes wrong. We're here, we invented DICE to make the estimation of higher order gradients in stochastic computation graphs as easy as possible. But hang on a second, what exactly is a stochastic computation graph? Funny you should ask. Turns out a stochastic computation graph is nothing but a formalism that lets us define the relationship between a set of nodes. In particular, a stochastic computation graph, or SCG, consists of three different types of nodes. We have the input nodes, and we have deterministic nodes, for example, cost functions, and stochastic nodes. In the little example on the right, you can see a function f, which is our objective, which depends directly on the parameters theta, but also depends on a variable x, which is sampled from p of x parameterized by theta. Before we get to the exciting high-order gradients, let's briefly remind ourselves how to estimate first-order gradients using the score function estimator. First of all, we're writing the gradient of the expectation and expanding it as a sum over x, p of x times f of x. When we differentiate through this, we're producing two terms. The second term is easy. It's p of x times blah, so I can sample x from p of x and just evaluate the estimate of the gradient of f of x. However, how do you sample from grad theta p? Well, that's more complicated. But luckily, we can apply the log likelihood trick by just rewriting grad theta p of x as p of x times grad theta log p. And now we're done. We're home safe because we have two expressions of the form p of x times blah, and we have another expectation. So this is our gradient estimator, which we can evaluate by sampling x from p of x in order to get an estimate of the gradient of the objective with respect to theta. And clearly, now no one can stop us from relabeling this term as G. And while I told you this was a derivation of the first order gradients, I claim that we're done, because we can just take G, replace f with G, and repeat the entire process to get the second order gradient estimators. However, this would be a very short ICML talk if this was the answer, and it isn't, because there's three things that are missing. First of all, we want this to be computable easily. We need to get these estimators out in a computational framework using deep neural networks. Secondly, we really like to have a surrogate objective. Because we're doing deep learning, I don't want to define the gradients, I want to define an objective function, which can be differentiated repeatedly to produce higher order gradient estimators. And that's the main idea behind the surrogate loss approach, which was the previous approach for generating these high order gradient estimators. It was invented by John Schumann et al. In 2015. And the idea here is we're going to take this little example we have. F of x depends on x and theta. And we'll construct a surrogate loss, which is this term, log p f hat plus f. The point of this term is when you differentiate with respect to theta, it will produce the first order gradient estimator. And this is achieved by adding this f hat term here, which means we've severed the dependencies of f on theta. The idea being that we do want a term of the form f times grad theta log p, but we don't want a term of the form grad theta f times log p, because that's not part of the estimator. And we need to have an objective that, when differentiated, produces the first order estimator, so we can call objective, minimized objective in our deep learning frameworks. And it's straightforward enough, in principle, to construct a second order estimator. All we have to do is take the first order estimator and produce a new surrogate loss, as shown below, where now our f was replaced with the first order gradient estimator. However, when we do this and we take the second order derivative, something interesting happens. In our example, f directly depends on theta. For example, if you're doing reinforcement learning, that's an entropy penalty. And we're now going to try and differentiate in the second order gradient estimator through f hat. But f hat means we've severed the dependencies of f on theta. So this term is going to be 0. So the bad news is, even when you've done all the hard work to construct a new surrogate loss for each of the possible gradients you care about, this surrogate loss, when differentiated, doesn't produce an unbiased estimate of the gradient because we're losing this term underlined in red. So there's two issues. First of all, you have to construct a new surrogate loss for each time that you want to create a higher order gradient. And secondly, even if you do the hard work, you're still going to get a biased estimator. And we're here to fix both of these issues with a mechanism called DICE. And indeed, if you look at what's happened in literature, people haven't really used the surrogate loss approach. Maybe because it's cumbersome, maybe because it's biased, although people didn't know. Instead, for example, in MAML, the authors just differentiated through the first order gradient estimator again. And that leads to wrong terms. There was a follow-up paper by Brady et al., which derived the correct second order estimator for this example and spent about a page doing maths. And then there was another paper by us, Learning with Opponent Learning Awareness, where we had to differentiate through the learning steps of other agents. And I can tell you, we spent about 3 weeks deriving and implementing what we think are the correct higher order estimators. So we're here to make this really, really easy for you. And you can do this using DICE. DICE is our answer to the problem. It relies on a new operator called the DICE operator. This DICE operator has two properties, which are somewhat magical. First of all, you feed in any sets of nodes of your stochastic computation graph, and DICE will evaluate to 1. You can think of this as the forward pass. Secondly, when we call gradients on DICE, it produces a gradient term of the form DICE times gradient of sum over log pw for all the w's in the input w. And clearly, this isn't really a function that maps from x to y. It's an operator. And what it does, it captures the dependency of our samples on the probability distribution that they were sampled from. So if you remember the derivation we did for the score function estimator, indeed, all the samples when being evaluated have a probability of 1. But when we differentiate in the gradient, we had to apply the log likelihood trick to get the correct estimator out. And this is what the DICE operator does. It has that same mechanics under differentiation as we observed in the initial slide that I showed you 5 minutes ago. Using this DICE operator, we could have defined the DICE objective, and that's nothing but the sum of all the cost nodes we care about, multiplied by all the causes for each of the nodes. And we prove in the paper that given those properties, if there was such an object like the DICE operator, then this objective has the property that any order gradients of the DICE objective are gradient estimators of the appropriate higher order gradients of the original objective. Now, luckily, this object exists. And it turns out it's not just any function. It's indeed nothing but exponential of tau minus top gradient of tau, which is readily available in all deep learning libraries. As you can see, exponential of x minus top gradient of x will evaluate exponential of 0, which is 1. And when we differentiate it, we will indeed reproduce the DICE operator as required. We want to have DICE times blah. And we'll get the correct grad theta log p terms as required by the first order and higher order gradient estimators. We can also extend this framework to include a baseline term, where we include a term of the form 1 minus DICE. 1 minus DICE evaluates to 0 on the forward pass, so the mean is unchanged. However, when we differentiate through it, we will get the correct variance reduction for the first order gradient estimator. Now let's compare for what this cumbersome example looks like in the DICE framework. In SL, we had to create a number of different objectives, differentiate through them to end up with a biased gradient estimator. In the DICE objective, we produce a single objective, the DICE objective, and then differentiate it once to get the first order gradient estimator, and can differentiate any number of times to get higher order gradient estimators in a computational framework. This is what it looks like in actual code. So we can see the DICE objective being defined at the top, and down here is nothing but the logic in reinforcement learning setting where we handle the causality between actions and rewards. The good news is you don't have to go and implement it, even that one line, because DICE now has been implemented in TensorFlow probability, where it's available in the Monte Carlo estimate, but also in Pyro, where it's available as DICE in the framework. Now let's look at an example for what this all looks like in reinforcement learning, because that's one of our main applications here. It turns out in reinforcement learning, the cost nodes are the rewards R, at each time step. So we have these different cost nodes here. And we multiply each cost node by the dice operator acting on the causal nodes. And those in RL are just the actions, right? Because we have this probabilistic graph which represents the causal dependencies between the states leading to actions and the rewards and to state transitions. And here we see that the dice objective is nothing but the sum of these terms at the bottom. We can sum all of these up and then differentiate them to get the gradient estimators. And that's what we use dice for in an RL setting. Now, it's obviously fantastic that we have a proof that this is all correct and right. But I'm not sure if we really trust these proofs. So therefore, we went back and actually looked at numbers comparing the exact gradient in a reinforcement learning setting with an estimate of the gradient. So what you can see in red is the exact gradient and in green the estimate. And what we find is indeed dice does produce unbiased gradients, but also Hessians. And to be clear, the right-hand side wasn't produced by doing a page of maths. The right-hand side was produced by calling tf.Hessians on the dice objective. And the left-hand side is nothing but tf.gradients. So we've drastically simplified the process for obtaining high-order gradient estimators in computational frameworks. We also investigated how the quality of the baseline, because that's a core part of the algorithm, changes the quality of the gradient estimator. And what you can see on the left-hand side is that as we get a poorer baseline, indeed, the quality of the gradient estimator starts to drop drastically. However, a good baseline can make a drastic difference because without the baseline, we need a large sample size of 20,000 to get a good gradient estimator. In blue, we can see that with a good baseline, we can get good gradients out even with a small sample size. And that's very reassuring. Lastly, we applied DICE to a setting of learning with Poland learning awareness, which is actually also a paper here at AMAS. It's going to be presented at 3:30 p.m. today at the poster session. Come over if you're interested. In Lola is a fascinating paper in which agents account for the learning behavior of other agents. And it turns out treating other agents as part of the environment doesn't lead to good outcomes. Humans differentiate between trees and other humans and cars. Wouldn't it be nice if other agents also knew what another agent is and what a car is? And in particular, accounting for the fact that other agents are also learning. And that's what the Lola learner does. In Lola, each agent imagines that the other agents are naive learners updating their parameters using standard policy gradients. And they then differentiate through this learning step. You can see how second-order gradients will appear naturally in the Lola formulation of the problem. In the original paper, we were concerned that differentiating through the learning step inside the computation graph would lead to missing gradients, which it does. In fact, the naive gradient, if you differentiate again, it's 0 with respect to the other agent. So instead, what we did is we did a Taylor expansion, where we expand the value function, looking ahead one step. And this led to the emergence of a second-order term here and a Hessian, and it led to about 3 weeks of struggling, bringing down the variance of this term, trying to do the right thing. Good news is you don't have to worry about it, because now we have a much cleaner formulation using the DICE objective, because now we can safely differentiate through the learning steps of other agents without losing the dependencies on the policies that created them. So using DICE, we can formulate Lola as a meta-learning problem, whereby in the inner loop, Alice is imagining the learning steps of Bob. And in the outer loop, we're differentiating the final objective after Bob's learning with respect to Alice's parameters. And that's indicated here. We have this learning step delta theta 2, which now importantly is the gradient of the DICE objective with respect to theta 2. And we're now looking at the reward using a policy which has anticipated the learning of Bob in the inner loop. And we can now differentiate this entire thing end to end, because when we hit the first order gradient with the next gradient operator, will produce the correct gradient estimates in the DICE objective. And the other agent here is doing the same thing. This is what it looks like in pseudocode. So again, if you're familiar with meta-learning, this is very much, now we've combined the Lola perspective with meta-learning. And in particular, in the inner loop, we're unrolling for k steps the learning behavior of Bob. So theta to Bob goes through naive learning here, updating their parameters from theta to prime to a new value, using the naive learning step. And then we construct a new rollout of trajectories in the outer loop, where we're looking at the return after Bob's learning. And the key part is that we can now differentiate through this entire learning process end to end, because we have access to the novel DICE operator. So for clarity, If this was the standard surrogate loss approach or the standard score function estimator, the first order gradient of Bob has no dependency on Alice, because the first order gradient estimator simply treats Alice as part of the environment. In other words, if you take log p of theta pi 1 and differentiate with respect to theta 2, that's just 0, because we've lost the causal dependencies. Using DICE, we can maintain all those causal dependencies. It turns out that not only does this provide a simplification from a conceptual point of view, we can bring together these different perspectives, learning with upon learning awareness and meta-learning, but it also has drastic implications on the parameter efficiency, on the sample efficiency of this algorithm. It turns out in the original paper we had to use a batch size of 6,000 to bring down the variance in our Taylor expansion, our Hessians, while in this new paper we can use a batch size of 64. So the results you're seeing here are for a batch size where all agents are using 64. The naive learners, to our great denial, learn to defect in the iterated game. So this corresponds to cars crashing into each other. In contrast, the Lola agents using this batch size of 64 didn't even have stable learning. They were all over the place in their policies. However, using the Lola DICE formulation, where we can differentiate through learning steps of other agents in an organic manner, we actually managed to get stable results of agents learning tit for tat in this iterated game, leading to a reward of minus 1 roughly. And the other nice thing here is we can now look at different steps of look ahead for the other agent, because this is now really meta-learning. With that, let's conclude. We found that DICE makes higher order gradient estimation extraordinarily easy. In particular, it lets us use the powerful tool of auto-differentiation in order to do graph manipulations required to get the high order estimators. It allows anyone here to do meta-learning. Basically, when you're done with this talk, go home and try some meta-learning because the code is online. And this includes multiple learning agents, or it could also be used for second-order optimization in reinforced learning settings. DICE has been implemented in Pyro and TensorFlow probability, so it's available for everyone to use. And we've made the code for the example that we've shown here available online at github.com/alchdevat/Lola. In the future, we would love to improve the baseline terms for the higher order gradients that emerge. And we're planning on applying DICE to a broad variety of meta-learning issues, including student-teacher settings, communication settings, multitask settings, and others. So if you're planning to work on this, be quick, because we'll also be there. The other idea is that we could also try and have a curriculum that teaches the environment how to facilitate learning in other agents. With that, I would like to thank you all for listening. Quick reminder here, the code is available online. Please check it out. And we will be at the poster 102 this evening. Thank you very much for listening.
We have some time for 1 or 2 questions. Please come to the mic. I guess they are somewhere. Okay.
Hello. I have a quick question. Does incorporating the second-order gradients, let's say, into supervised setting, how does it perform in terms of speed of the learning and that stuff?
Yeah, so to be clear, our work is focused not on the supervised learning case, because you have the correct high-order gradients if you want them. So this is really looking at reinforcement learning, or other cases where you have to estimate gradients using samples. And in general, the computational cost here is tractable as long as you can bring down the variance. And that's something we're investigating actively right now. How can we have better baselines for the high-order gradient estimators?
Thank you.
Can the next speaker come and start setting up? And we can take one more question if somebody has another question. The next speaker can set up. So I have one small question, actually. Have you actually tried to implement this for something like a Newton method? And do you know if you see a good performance there?
We haven't yet. I think that would be a fantastic thing to try. We did investigate Newton method a little bit, because in the Newton method, we found that using the surrogate loss approach, you actually drop one of the relevant terms. And we found that, at least on paper, DICE gives you faster convergence because you have an unbiased estimator.
Makes sense.
But I think there's a lot of open work here. Really, we're trying to bring high-order gradients to reinforcement learning in as painlessly a way as possible.
Thank you. Let's thank the speaker again. So our next speaker is Theo von Weber, and he'll be talking about learning to search with MCTS nets.
Thank you. So I'm Theo Weber. I'll talk about learning to search. And this is joint work with all these wonderful colleagues at DeepMind. So we place ourselves in a context of search, which I will define roughly as iteratively considering different solutions for a problem for which I have some kind of evaluation function, and using information from the previous candidates to identify an optimal or as close to optimal solution as possible. And so we know this has many applicable domains. Famously, it was used in AlphaGo and AlphaZero. It was used recently to solve the Rubik's Cube, used for chemical synthesis, machine translation, and so on and so on. Traditionally, though, the search algorithm that we use rely on hard-coded rules and heuristics, which were derived from human ingenuity and mathematical derivations. And so the question we ask is, could we learn to fine-tune a search algorithm for a particular class of problems? Can we effectively, for a problem that I care about, derive a form of intuition about how to search? So that's what and the hope would be that this would lead to more effective search because we could learn, improve information flow between the candidates that we consider, learn a representation of uncertainty about whether a line of search is actually going to give good results, and learn to tweak the trade-off between exploration and exploitation. So our approach starts from an existing successful algorithm, Monte Carlo tree search, where the name MCTSNet comes from. And so we keep the algorithmic skeleton. We're going to identify subcomponents of MCTS, and we're basically going to parameterize the subcomponents and learn them. And so the meaning of a subcomponent will be given by how it is reused across the network. We're going to train the network end-to-end by optimizing a chosen loss function, and we chose a particular one, but there are many possible ones. And so in terms of difficulties, there's two main ones. The first is that you have a highly dynamic computation graph because you're building a tree. So there's a lot of conditional computation going on. And the second is the credit assignment issue, because ultimately all I care about is my final solution. That's the quality of the solution I care about. But getting there, I explored lots of different solutions which maybe contributed towards getting to that final solution. And so how do I give credit to exploring maybe a suboptimal solution but put me on the right way? So I'll give a very, very quick primer to MCTS. So MCTS is an algorithm that works with multiple simulation. I start with a single simulation halfway through the search. And you have here this large triangle here, which represents the current state of the tree. And in every node of the tree, you have a number of statistics. In MCTS, you have the Q function for each action, the visit count, and potentially policy prior. And so the first phase of the simulation is the tree traversal. We're going to go down the tree from the root to the nodes at the boundary, which have not been explored yet. And in the AlphaGo style framework, they use the UCB type rule, which is a fixed function of Q and the prior network, which is written here. So you go down the tree that way up until you reach a node at the frontier, and then we enter the expansion phase. So the first thing we do is we've never seen that node, we've never seen that state, so we evaluate how good of a state it is using a value network. And then we expand, which means we add the children of that node to the tree. We don't explore them, but we consider them for future traversals. And then the third phase starts, which is the backup phase, where we go back from this leaf node up to the root. And so this is the phase where the statistics get updated, and namely, the Q functions get updated in the direction of the value function of the leaf node, and the visit counts get increased by 1. And so you do this for a large number of simulations, and eventually what you do is to take the maximum Q or the maximum visit count at the root node, and that's your candidate action. So that's MCTS. In MCTSNet, we're going to follow a similar framework. So again, it's a many simulations-based algorithm, and we have a tree. And the difference is that in every tree, we have, instead of fixed statistics, we'll have an embedding. And I'll explain in a bit how we get that embedding. And the first phase is, again, the traversal phase. And so from the embedding, we have a little network, a simulation policy network, which computes probability of taking the different actions, and we sample from that. And we use that network to traverse down the tree, using the true model, up until a leaf node. At this leaf node, we have never explored, we have never seen, and so we need to initialize the embedding at that node, and so we use an embedding network to initialize the embedding. We expand, And then we do the backup phase. And so the backup phase is going to update every embedding of the nodes that we have visited in that particular simulation. And so these backup networks takes two input. It takes the previous value of the embedding and the embedding of the child. So you go up. So this embedding here is a function of its previous value and the child. And so you go up the tree up until the root node. And so that's a simulation. So this is a pictorial representation, again, of the forward and the simulation in the backup phase, going down the tree using the expansion policy and going up the tree with the backup network. Now you do many simulations. So as a network, MCTSNet builds, effectively incrementally build a large tree and does a lot of simulation and backup phases. So it looks like a gigantic network with lots of sharing and a lot of skip connections, basically. And at the end, you take the embedding of the root, you have a readout network which gives you some sort of output, and using side information, you compute the loss, and you differentiate through the whole network. So this is a recap of the 4 modules that we need, which are, we kept pretty small, actually. The 2 first are used to propagate information between the nodes of the tree, and the 3rd one is used for the construction of the tree. The readout is just to come up with a final answer. So the problem we evaluated is Sokoban in a classification setting. So Sokoban is this classical planning puzzle game where the little green character here pushes boxes onto these red targets. And because it can only push the box but not pull them, this leads to a lot of difficulties in terms of puzzle. So we constructed a data set of input-output pairs where the outputs were oracle actions, which are obtained by running a long, large-scale Monte Carlo tree search. And so the question is, can we learn to replicate the effects of that large, kind of slow Monte Carlo tree search with only maybe a few simulations instead of thousands or tens of thousands? So the loss, it's classification, so it's across entropy, but there's a catch because there's many internal actions, internal stochastic actions. So really what you would want to do normally is to integrate out all the internal stochastic actions, all the expansion actions that we took. And this is hard, so we just use an upper bound to the loss, where we sample the internal actions from the networks that I mentioned. And when you differentiate that loss, you obtain 2 components. One is the straight-through estimator, so all the differentiable parts, which are the embedding network and the backup network, are always differentiable. But the expansion network, because it samples an action, is not differentiable, and so we trained it with reinforce, even though we do a classification problem. So the classification loss acts as a pseudo-reward. And reinforce by itself is not strong enough. It has too high variance. So we introduce a credit assignment technique for any time algorithm, which I won't go into the details of. These are a summary of the results. So the first 3 that I want to highlight is a straight line, which is MCTS with UCT. The lowest line is 25 simulations. Here you have 100 simulations, and the top performance here, about 85% of level solved, is at 500 simulations. And the blue line here is MCTSNet with 25 simulations. So you can see that MCTSNet, even though it uses an order of magnitude lower number of simulations than MCTS regular, effectively achieves about the same performance. So now you could say, well, this has maybe nothing to do with search. It's a big network. If there's a lot of sharing, but it's a big network. So maybe a similar network just feed forward would have gotten the same performance. And so we evaluate this by taking the MCTS network and replacing the model by just a copy operator, which copies the frame. And so if we do 2 simulations, you get a network with the exact same number of parameters, but fewer operations. And it's the red curve here. And if you do 25 simulations, you get exactly the same architecture with the same number of parameters, the same number of operations. The only difference is that the model itself doesn't do anything. And you can see that the performance is much lower. So effectively, MCTSNet does take advantage of the simulation of the information that it aggregates by expanding the tree. Very quickly, it's a planning algorithm, so you can actually increase the number of simulation without increasing the number of parameters. And so here I color-coded in blue, the darker, the more number of simulations. You can see as you increase the number of simulations, you learn both faster and better performance. So in conclusion, if we learn to search and train it on a specific problem, we can learn to improve performance compared to classical search techniques. We exhibit a planning lag behavior with the network, and that is the performance gets better if you throw more computation, but not more training data or more weights, just more amount of time. And we introduce a credit assignment technique that helps train anytime algorithms. There's a number of open questions. Can we use it with a learned model, maybe an implicit model, an explicit model, and can we modify MCTSNet to deal with partial observability? That's it, and the poster will be tonight. Thank you.
Unfortunately, we don't have time for questions, but I'm sure you can visit the poster and talk to them about their research. So the next speaker.
Thomas Mikoni.
So the next speaker is Thomas Mikoni, and he'll be talking about differentiable plasticity, training plastic neural network with backpropagation. I'll give you a signal when 1 minute is left.
Hi, so my name is Thomas, and I'm going to tell you about differentiable plasticity, which allows us to train plastic networks with gradient descent. But first, I'm going to discuss why we will want to do that. So as you know, in deep learning, usually the standard model is that you have a large network which you train slowly, incrementally, once and for all over a large number of examples, thousands, hundreds of thousands, in order to incrementally reduce the error. And after that, usually the training is done and there's no more learning. By contrast, animals are able to learn very quickly, very high dimensional information, sometimes with a single exposure. At the bottom, you see a little mouse exploring a maze that it has never seen before. And once in this maze, the little mouse finds this cache of seeds here, it learns very quickly to go back repeatedly to that cache of seeds. So it has learned quite a complex trajectory, which is quite a high dimensional information, extremely quickly. Now, this ability is not an accident. It has been carefully implemented by evolution, the long-term design process, in order to endow us with those very fast, lifelong learning abilities that we have. Now, the problem of training networks so that they can keep learning during their lifetime autonomously and efficiently is a problem of learning to learn, or meta-learning, and there are many methods for this, which I don't have time to enumerate here. But in animal brains, the main support for durable memories is thought to be synaptic plasticity. That means that the connection between any two neurons changes automatically as a result of activity. Most of this plasticity, most of those automatic plasticity changes are Hebbian. That is, I follow the so-called Hebbian rule, which is generally very roughly summarized as cells that fire together, wire together. And again, the crucial point is that this plasticity is not haphazard. Evolution has carefully sculpted not just the baseline weight, but also the plasticity of each individual connection in the brain, well, at least each group of connection, in order to induce this fast, lifelong, efficient learning that we have. Now, there has been some work on training plastic networks, but usually either the plasticity itself was not trainable, it was a fixed parameter of the network, homogeneous for the whole network, or when plasticity was trained, it was usually with evolutionary algorithms, which were generally low-dimensional and restricted to small neural networks. So what we want to do is be able to use gradient descent to train not just the initial weights, but also the plasticity of each individual synapse in the network. And the reason we want to do that is because we hope that it will bring us a little bit closer to those fast, lifelong learning abilities that evolution has ingrained into animals. So to do that, all we need is a differentiable specification for Hebbian plasticity. There are many ways to do it. The way that we have chosen is as follows. So here, every connection between any two neurons, I and J, has both a fixed component, here in green, and a plastic component, in red. You recognize the standard equation for neural network. So this is the total weight of any given connection. The fixed component is just the baseline weight. The initial weight is just a normal weight, as you will have in any neural network. The plastic component is the product of this so-called Hebbian trace, which implements the actual plasticity, multiplied by a size parameter, alpha. The Hebbian trace is computed according to this equation here. It's just the standard product of input by output, the standard Hebbian equation, with just a decay term here to prevent it from going to infinity. This is just one possible implementation. There are many others who have implemented other plasticity rules, Oya's rule, neuromodulation. This is just the simplest one here. Now, how do we actually use that for learning? H, the Hebbian trace, the plasticity of each connection, is a lifetime quantity. You initialize it at 0 at the beginning of each lifetime/episode, and then you update it automatically as a result of ongoing experience, according to this equation. At the end of each episode, you get a loss, and what you compute is the gradient of this loss over the parameters W and alphas, the fixed baseline weights and the plasticity coefficients. Those are the structural parameters which you are going to train and optimize in order to induce fast, efficient learning abilities in the network. So, I just note that it's extremely easy to implement. This is a standard recurrent neural network implementation. To make it plastic, all you need to do is to add the lines in yellow. Just 4 lines of PyTorch and your recurrent network is plastic automatically. All the code is online, you can check it by yourself. No second order gradients or anything. So first task, of course, it's meta-learning, so we implemented the Omniglot task, that's called MNIST of meta-learning. So this task consists in classifying unknown 100 characters. That is, I show you 5 characters, each with a label. So this is character 1, this is character 2, this is character 3, etc. And I show you a new instance of one of those characters, and you must tell me the label. The trick being, of course, that you have never seen those characters ever before. So you must learn quickly to associate those shapes with the labels. So the architecture that we chose is we simply took the standard convolutional embedding for this task, a 4 layers convolutional network with a softmax on top, and we simply put plasticity in the top softmax layer, to which we also feed label information. And that's it. And just with this simple approach, just making the top layer plastic, we get results which are competitive, at least, which with considerably more complex approaches, including MAML and the snail method, which involves a temporal convolution with many more parameters on top of the embedding. So that's encouraging. Another experiment that we did is one of image memorization, that is memorizing very quickly high-dimensional patterns. Here, the task is to memorize images and to reconstruct missing portions of them. That is, here, each episode is shown vertically. I show you 3 images, and then I show you a degraded version, sorry for that, of one of those images. Here, degraded means that half of the image has been removed, either the top or the bottom half. And what you need to do is to reproduce the missing portion of the image. So you need to memorize those images that you have never seen before quickly, just from a few exposures, and regurgitate them when prompted with a half image. The network is a standard recurrent neural network with 1 neuron per pixel. You see that it works pretty well. There's roughly 1,000 pixels per image, so it's 1 million connections and 2 million parameters. So differentiable plasticity works on large networks. But perhaps more interestingly, for those images, standard non-plastic networks fail miserably. LSTMs cannot solve this task, as described here. They can learn a much simplified version of this task, where you only have 50 bits in binary patterns, and even then, as shown on this graph, they learn quite badly. This is, in green, the standard RNN with no plasticity, fails. This is an LSTM with no plastic connections and with a lot more neurons, and even then it takes a lot of time to learn. In blue, you see the standard RNN with plastic connections. It learns almost immediately. It's difficult to make starker contrasts. So finally, we wanted to see whether it will work on reinforcement learning settings as well. So we had this very simple task with a maze exploration task, where you must find the reward. You are the agent in yellow. You must find the reward in green. And you must not only find it, but also navigate repeatedly to it. And at each episode, the reward is positioned at a random location. So you must memorize and repeatedly navigate to the location of the reward. And we see that here, again, plastic networks significantly outperform the non-plastic network. Plastic networks are in blue. The same architecture, but without plasticity, is in red, and it learns very badly. And just to confirm, It only works if you can train independently the plasticity of each connection. In red, you have the exact same thing, but where all the connections share the exact same plasticity as a homogeneous shared parameter, and it doesn't quite nicely as well. So in conclusion, gradient descent can train the plasticity of very large networks. It works very well in supervised or reinforcement learning settings, and it's extremely easy to implement, as you can see yourself by checking the code on GitHub, and it offers a flexible, nature-inspired method to the meta-learning problem. Thank you very much.
Thank you. Unfortunately, we don't have, again, time for any questions, but please go to the poster and talk to the authors. So the next speaker is, I need to make sure if I get this right, Kyriakos Sherlis.
Yes.
He's going to talk about TACO, learning task decomposition via temporal alignment for control.
Hello, everyone. Very nice to be here, present our method, temporal alignment for control, which was developed along with my colleagues back in Oxford University. And it's a method for performing modular and zero-shot learning from demonstration. Now, in learning from demonstration, you can get away with basically not designing a cost function, hopefully, and then optimizing it, only by providing some demonstrations to a robot, and then hopefully it will be able to replicate those demonstrations, and then you have exactly the policies you need to solve the task. Now, there are, of course, a lot of challenges with this. For example, if we have hierarchical demonstrations that decompose into simpler subparts. For example, here we have a robot that is pressing down on some pin pad, and is pressing down a large number of numbers. But we know that we could decompose this policy that we observe into the individual button presses. So for this reason, we have something called a modular learning from demonstration that decomposes demonstrations that we see into smaller subparts. And this allows for more data efficiency. It allows us to reuse the policies that we learn. It allows us to be much more interpretable because we know what parts of the demonstration mean what. And it makes the learning of the individual policies much more easy. Now, the problems with this is that first you have to model what you want to decompose your policy into, your demonstration into. You have to decompose that demonstration into those parts, and then you need to perform learning for each one of the policies that you want to learn. And if you're coming from like a robotics perspective, you will say, I'm gonna parameterize this demonstration into some library of motion primitives, and then they're going to be quite flexible, and then I'm going to fit them into the demonstration, and that will give you a very interpretable and easy to synthesize method. You're going to be able to generate motions, new motions, very easily. Now, this will also constrain you, though, because it will make you also quite domain-specific and requires a lot of feature engineering. If you're coming from a more machine learning perspective, you will say, I'm going to model these subparts within the demonstration as more like a latent variable, and then I'm going to model the policies as some kind of differentiable architecture, and then I'm going to have a very general method, very powerful. But that would make it very hard to interpret what these latent variables are and hard to synthesize new motions. And in this work, we aim to achieve the best of both worlds between these two perspectives. And we do so using task sketches, which is related to policy sketches introduced last year at ICML by Jacob Andreas. And from that work, we take two concepts. We take the notion of a task sketch, i.e. a vector that accompanies the demonstration and gives us what subtasks are within the demonstration and their order. And then, for example, for the previous task of the robot pressing down on a pin pad, we will get a vector saying press 1, press 2, press 5, press 3, accompanying the demonstration. And we also have self-terminating policies, i.e. policies that are augmented by a stop action that can terminate themselves, And after that stop action is called, the next policy within the sketch starts to be executed. So how does it look for learning from demonstration? We have demonstrations here in red of length capital T, a very large number usually, and task sketches of a very small number, L. In this case, is only 3. And then we would like to learn self-terminating policies for each one of the symbols within this vector that we're getting, this task sketch. And then we want to be able to compose these policies to execute new tasks. And the main challenge we have here is that basically the task sketch and the demonstration are not aligned in any way. So we don't know when the stop action is being called within the demonstration, and the demonstration and the task sketch are in different time scales. So we need to align them. So somebody might say, okay, let's perform alignment first. Let's use something like connectionist temporal classification that maximizes the likelihood of the observed sketch given the demonstration, and that would give me an alignment for the task sketch and the demonstration, and then I'll be able to decompose that demonstration into small data sets, one for each of the symbols that I want to learn, and then I can perform something like behavioral cloning in order to learn the mapping from states to actions, i.e. my policies. Now, if you do that, the problem is that there is no inductive bias within the alignment that you're going to use these decomposition in order to learn policies afterwards, i.e. the policy learning step cannot influence the alignment. And so a much more sensible approach, which is exactly what TACO does, is to optimize the joint likelihood of the task sketch and the actions given the demonstrations. And this gives us exactly what we want. The policy learning part can influence the alignment, i.e. it can basically choose what each policy can choose what data points it is better at fitting. And then there is this inductive bias for control that we want. We are maximizing for better control, not for better alignment, hopefully improving both. So how do we do it? Basically, we put the self-terminating policies directly into the dynamic programming step in the same way that connectionist temporal classification does. And the initialization of these forward variables at time step equals 1 is basically the probability that we observe that the first action given the first state for the first policy and the rest of the forward variables are 0 because we know that we are constrained to start at the first policy. Then for time step 2, we can either choose to stop, at which point we go to the second policy within our task sketch, and we multiply that probability with the probability of observing the second action given the second state for the second policy, or we can choose to stay at the same policy, at which point we multiply that probability with the probability of observing the second action given the second state for the first policy, because we remained at the first policy. And we continue this recursion forward, and then at the last node of this computation graph, we get the quantity we need, which is basically the likelihood of observing the task sketch and the sequence of actions given the state, and at which point we can just maximize it. So that's all great, but how does it do? In the paper, we have many domains to show basically that TACO is domain agnostic. You can apply it to robotics, you can apply it to like arbitrary agents. But here we present this Jaco dial domain that we've seen at the beginning of the talk, where you have a robot, you observe these button pushes on this pin pad, and your sketches are what buttons have been pressed. And then at test time, we have a new sketch that is given, which we are supposed to execute, at which point the task is considered successful if we execute all the subparts, basically. And then what we see is that as we increase the training data size, the performance of TACO in red here approaches Oracle performance, i.e. the performance as if we would be given exactly the alignment between the task sketch and the demonstration, which shows, but with much less supervision, of course, we're not given the alignment. And we also see that if we increase the task sketch length, TACO also seems to be more robust than the Oracle in this case. And we believe that this is because we are optimizing over probability distribution of our alignments, which gives the policy view of many more data points, which introduces a regularizing effect. Now, we also have results on the accuracy given, on the alignment accuracy of the method, given new test pairs of demonstrations and sketches. So in conclusion, we have a TACO which simultaneously learns to align sketches with demonstrations and perform control. It is general, it is interpretable, it can be easily controlled and is weakly supervised, and it outperforms naive approaches and reaches Oracle performance as more data is given. Thank you very much. Come to the poster number 52. And yeah, I guess we don't have time for questions.
Yes.
Thank you.
Thank you. The next speaker is Alvaro Sanchez Gonzalez, and he's going to talk about graph networks as learnable physics engines for inference and control.
Hi, everyone. I'm going to be presenting our paper, Graph Networks as Learnable Physics Engines for Inference and Control. Why do we want learnable physics engines? Mainly so we can roll out good trajectory predictions, which can be very useful for model-based planning and also useful to maybe estimate policy gradients if you're trying to train a policy. And we want flexible models because we want to be able to deal with things like partial observability of parameters, maybe via system identification. So the kind of systems I'm working with here are actuated systems, most of them coming from the DeepMind control suite. They are implemented in MuYoko. We're also working with the system of a real robot arm, as well as the actual real robot arm. So what you see in this video is these systems under the actuation of a random agent. I would like to remind you that all of the work that we do in this paper, all the training that we do it from data training, from data obtained by running a random agent of these systems. But you'll see that later, even though the data is from random agents, you can get control sequences that solve certain tasks. So what we did differently in this project is that instead of flattening all of the input observations and actions as you will do in more classical models, we decided to store them in a graph. Why we will do this? Because this is essentially how physics engines work. A physics engine will take the kinematic tree of the system, will consider pairwise relationships between the different bodies, will propagate forces little by little through the system to come up with the right dynamics of the system. So what we did this in particular here was to take all of the bodies in the system and transform them into nodes, putting all of the features of the bodies as node features. Then we'll take all of the joints of the system, transform them into edges, again, putting all of the joint features in those edges. And finally, we also had a set of global features associated to our graphs that will contain things like the time step and gravity and stuff like that. So the fact that we're setting observations in a graph, this is not a completely new idea. There's been prior work that has done this in the past, including interaction networks, where they did this to learn models of simpler systems that were non-actuated. And also recently, earlier this year, NerveNet used a similar structure of observations to learn a policy to control some of these systems. But now that we've put our observations in graphs, the next thing we need is a network that can actually process these graphs. So what we did here was to use this new framework that we termed graph networks that was both introduced in this paper and another paper that we published a couple of months ago in arXiv. That is a reference up there. So the idea of this framework, which is not completely new, is try to unify most of the existing frameworks that we'll use to take graphs as inputs, including message passing networks, relation networks, interaction networks, non-local linear networks, networks working on sets like deep sets. But the idea here is that our networks are made of composable modules that takes graphs and also output graphs. So you can compose multiple of these graph network blocks together in depth to get deep graph networks, essentially. So internally, graph networks are made of 3 different blocks. They have first an edge update, which is a function that is applied to every edge on the node. So it's a serve function that will take the input edge, all of the nodes adjacent to that edge, and the graph features, and produce a new edge. And the magic here is that the same function is applied to all of the edges in the graphs. Similarly, you do the same thing for the nodes. Now you take a function that gets applied to every node, considering all of the edges that are adjacent to that node and the global feature vector, and produces new nodes. And then similarly for the globals. But now all of this sharing that we have in this network on an edge level and also on a node level, what gives us is an inductive bias for entities and relations in our models. It makes our models to want to learn about entities and relations, and also to benefit from all of the shared dynamics that you know between pairs of objects in your system in the same way physics engines do. So this typically leads to improved data efficiency because as opposed to an MLP where you will have to learn for 2 different inputs, that those inputs represent the same thing and that follow a similar logic, in this case, you automatically get this because you're applying the same function to all of the nodes in your graph. Furthermore, you get advantages such as compositional generalization, because for this kind of models, they only care that you put graphs in the input, but they don't tell you anything about this particular size of shade of the graph. So you can do things like testing in a graph with 5 nodes, and then evaluating in a graph with 10 nodes or 15 nodes, and get generalization for larger structures. So the first type of experiment that we did here was to try to learn one-step forward model, where we will take an input graph that will contain both information about the state of all of the bodies and also information about static parameters of the bodies, and then process these graphs using 2 sequential graph networks connected like you see in the top right of the screen. And then this will produce an output graph that is meant to represent the state of the system at the next time step. So what you see in this video, in the video on the right, is what happens when you change 100 of these predictions from the previous prediction, and then you can see that essentially you can get a very, very accurate trajectory that matches very well at the ground truth trajectory that is shown here on the left. So we were wondering at this point, how much better is this than just like the equivalent MLP model? So we ran some baseline experiments for each of the systems, and the first thing we observed is that as the number of repeated structure increases in your system, then the relative performance of the graph networks becomes much better. And not only the relative absolute performance, but also the generalization. So technically what we observed is that our models generalize better, not only to validation data obtained from the same distribution of another random agent training running the same system, but also to data generated by a DDPJ agent policy trained on solving a task on one of these systems. So it's really generalizing much better to other data out of distribution. So as I said before, you're not constrained by input graph size. So something else you can do is to train a single network on more than one of these systems. So this is what we're seeing here on the top. I'm showing here a single model that was trained on Pendulum, Carpol, Acrobot, Swimmer 6, and Cheetah and WANS. And you can see that the predictions are accurate for all of them. And furthermore, what you can do is what I mentioned before. You can do compositional generalization. So in the bottom, what you see is a swimmer of variable lengths. And then for training, we only trained on swimmers with lengths 3, 4, 5, 6, 8, and 9. But then we evaluated on swimmers with 7 and more than 10 links. And as you can see in the video, all of these zero-shot predictions for links never seen during training are actually pretty accurate all the way up to 15 links. We also tried more on real robot data, and in this case, we only had to make a small adjustment to it to make it recurrent with a small graph GRU core. But after we introduced this, essentially, you can see that it works pretty well in real robot data. Here, I'm just using Murioko to render the trajectories, but all of these trajectories are from a real grasping task controlled by a human in this case. And also, we had another part of the project dealing with system identification, which I won't have time to explain in length. But essentially, it consists of observing, getting to control a system with parameters that you've never seen before and without knowing the parameters. So we give a 20-step ground truth dynamic sequence of the state to our model. This is processed by a recurrent graph network. And then after inferring some abstract graph of abstract parameters, it's able to use this graph to then make accurate predictions for that same system learning. So this is what's happening in the video. First, you have this ID phase, where you identify the system, and then you have this prediction phase, where you can make a long rollout prediction for this system. So after having observed that our model can have pretty good accurate predictions, then we wanted to try this in control. So the first type of control we tried to use was a model-based planning, which consisted on essentially finding the sequence of factors that will maximize a given reward. So in this case, for example, in the JCO arm, we tried to get the JCO arm to imitate a given pose, which is shown in the left. And the task is to come up with a set of actions that, when applied to the motors, will take you to that pose. So as you can see, the model can plan very efficiently with the learned physics models, and then apply the actions in the real environment, and actually arrive at that pose, which was the target pose. You can also do control with the system that we train multiple systems. So we have a single learned network model here being used to control Pendulum, to essentially balance Pendulum, to lift up Acrobot, to also balance Carpol, to make Swimmer swims towards the target, and also to make Cheetah run towards the right. You can also do the same in a zero-shot settings, same way you could do zero-shot predictions for swimmers with 7 links and more than 10 links. Now you can do zero-shot control of these swimmers. And in this case, it starts failing with about 14 links, which is kind of where the model is starting to break for control, even though it was showing plausible predictions. Finally, because you're just doing model-based planning, now you are not limited by the kind of reward you're trying to enforce. So you can have a single model trained on one of the systems to now maximize different kind of predictions. So you can make, for example, both the cheetah system run, but you can also make it jump or move its torso, maximize the angular velocity of the torso, and similarly, you can get the walker to move forward and also to do headstands. Of course, it doesn't run very elegantly because it was only trained from random data, but still, it does the right thing. So this is it. I hope I've convinced you that we managed to learn models that are pretty accurate for forward prediction that can be used for system ID and control. I'd like to emphasize that this also works in real robot data and also multiple systems at once, so it gives you lots of flexibility, and it really supports control. And finally, I would like to emphasize that lots of this is thanks to the relational inductive biases introduced by graph networks, the model wants to learn about this relationship, and that this allows zero-shot generalization to new structures. So if you're interested, please come to see our poster this evening, number 84 in the Hall B. Thank you.
Well, unfortunately, we don't have time for questions. But let's, before we leave, let's thank all the speakers by clapping. So we'll meet again at 1:30 p.m. Enjoy your lunch.